Okay, welcome back, nerds. Today we're going to be talking about big O notation. So, what is big O notation used for? Well, it's mainly used for giving a rough time estimate for an algorithm. Along with that, comparing two or more algorithms. It can also be used to show memory usage for something. So, how would you calculate big O? Well, you show it as a function, and really, it's a little weird to get your head around, but once you understand it, it's pretty simple and straightforward. Really, you do something like counting how many times a simple function or basic thing happens. So, like in a sort algorithm, you would count up how many times a comparison happens. And because it's used for a rough estimate, we're only showing the biggest polynomial. So, something like 2n cubed plus 5n squared plus 3n plus 5 would just be big O of n cubed. So that means sometimes one algorithm could be faster than another, but the big O shows the same. It's really not that big of a deal. Chances are they're going to be pretty close together, and there's going to be bigger issues with one algorithm compared to another than just its like average big O. So let's kind of go into some common big O's. So big O of one, called constant time. It's just something takes like a set amount of time. It doesn't matter on the size. So checking if Boolean is true or false, indexing into an array, checking if number is even odd, something simple like that. Just we have log n, which is logarithmic time. This really good, pretty hard to hit. The example is binary search. There's not really many examples of it. Another day we'll probably go into binary searching and binary trees. We have big O of n, which is linear time. This is pretty common. This is usually like kind of what something could best be. So finding a highest value in an array or like a lowest value, indexing into a linked list. Generally speaking, anything that's just looping over something once with a for loop is going to be big O of n. Then you have big O of n log n. That's quasi-linear time. So this is pretty good. It's a little worse than linear time, but it's still pretty good, especially for like comparison sort and quick sort and merge sort. Those are really fast sorting algorithms, but as it shows, like best case, so it's not always going to run that fast. We have big O n squared, quadratic time. This is also a super common one. Bubble sort, insert sort, or insertion sort. Generally, anything with a nested for loop is going to be quadratic. Thing. Just because you see two for loops doesn't necessarily mean it's going to be like quadratic. Like, say you're trying to find the biggest integer in a 2D array. Well, you're going to need to do a nested for loop usually, so it doesn't automatically make it quadratic. It's just kind of like a way to start. Okay, finally, we have big O of n factorial, factorial time. So, example is like brute force for the traveling salesman. N factorial is like massive. It gets huge really quick. If you ever see like an algorithm's going to be n factorial, like try to figure out something better. Sometimes it's necessary. Sometimes there's no better way to do it, and it's not horrible when it's only a few values. But if you're like doing something on like 50 to 100 or even higher, like it's just gonna like bog everything down. It's gonna be slow. So I guess that's really it for today. The reason I didn't show any code for today is next week I'm going to go over a bunch of different sorting algorithms, so I figured I can that'll be a bit of an extension of this video, because whenever I'm going to be talking about algorithms, I'm going to be sharing big O information, because that is an important part of algorithms. So have a good day. If you have anything you'd like to see, remember you can always let me know below. Thanks. Have a good day.